Dear students, in previous videos, I explained you the strength of organic acids. Now, from this video, I'm going to start the strength of organic bases. So, strength of organic base that is determined by considering the following equilibrium reaction. So, base reacts with water. It abstracts the proton from water and it forms a conjugate acid, and OH minus is the conjugate base. Now we have to talk about the basicity regarding with this conjugate acid. In previous videos, we talk about the conjugate base. Whenever we want to talk about the acidity, so we have to focus on conjugate base. Now, as we are talking over here, it's a strength of organic bases. That means we are going to focus on the conjugate acid. The equilibrium constant for Kb in water is given by this equation, that Kb is equal to the product of concentration of the BH plus and OH minus divided by the concentration of base. So water that has been taken as a excess amount, so that is not going to consider here. Now organic bases, how we define the organic bases. So from the theory, that is Lewis acid base theory, the compound which donate the lone pair of electron, that compound is called as a organic basis. So whatever the three theories are there that we already discussed in the previous videos. Now here, first of all, I am talking about the aliphatic bases. So aliphatic bases, which are the different factors responsible for the strength of aliphatic bases? So the first one is strength of organic bases depends on electron donating effect. When we talk about the strength of organic acid, generally every time we talk that presence of electron withdrawing group, hence because of the electron withdrawing group, it stabilizes the conjugate base, hence as the base, a conjugate base is stable, then rate of dissociation is fast, and that's why it is a strong acid. Now, whatever the terms we discuss under the heading of strength of organic acid, exactly opposite terms now we have to discuss here, that strength of organic bases now here depends on electron donating effect. So automatically, if the electron donating effect increases, the basicity also increases. So which effect, that is electron donating inductive effect or electron donating resonance effect, increases the electron density on donor atom. So in aliphatic bases, organic bases are those compounds where which heteroatom involved in organic bases, the nitrogen as a heteroatom involved in the compound, so that is a donor atom. So nitrogen is a donor atom, and to this nitrogen atom, whatever the groups are attached, if that groups are showing electron donating inductive effect or electron donating resonance effect, then what these groups will do? These groups transfer its electron density to the donor nitrogen atom. Because of that, what happens? There is a excess of electron density on the donor atom. So more the electron density on the donor atom, more the capacity of donation of electron. So as you increase the electron density on donor atom, automatically that atom having a more capacity to donate the electron. As the donation capacity increases, so as per our definition, what is a base? The base is that compound which donate the lone pair of electron. So as the donation capacity increases, the basicity also increases. So exact opposite statement now here we have to use. In case of acid, what we say that pK, larger the pK value, weaker is the acid, or smaller the pK value, stronger is the acid. So exact opposite statement here we have to use for the basicity. As the pK increases, the basicity also increases. So larger the pK value, stronger is the base. These are the factors responsible for the strength of organic bases. Now let us take some examples. So here, first factor we are talking about the introduction of electron donating group which are attached to the nitrogen atom, and that groups are showing electron donating inductive effect. So plus I effect you can see. So first example is ammonia, the second is methylamine, third is dimethylamine, then fourth one is trimethylamine. So pK values are given 9.25, 10.64, 10.77 and 9.80. So from the pK value, as the pK value goes on increasing from A to C, that indicate what? From A to C, the pK value goes on increasing, indicate as the pK value increases, the basicity also increases. But look at the D, the pK value decreases. So it is in between 10.64 and that 9.8. So it is a weak base as compared to B, as compared to C, as well as it is a weak base. The reason behind is 10.64. So stronger the pK or the larger the pK value, stronger is the acid. So we call this as this amine is a primary amine. Methylamine is primary amine. Dimethylamine is secondary amine, and trimethylamine is a tertiary amine. So you can you see there is a, which is the stronger base? 10.77, that is secondary amine is a strong base as compared to the primary amine. Then next to that is tertiary amine, and the last one is the ammonia. So which effect you can see here? In ammonia, there is absence of methyl group, while remaining all the structure, there is a presence of methyl group. Now, another factor is what we see here, that number of methyl groups goes on increasing from structure A to B. As the number of alkyl group increases, means what we expect, the electron donating effect also increases from A to B. So electron donating effect increases the capacity of donation of electrons on nitrogen atom. So just now I already explained the donating group. What is the role of donating group? It increases the electron density on donor atom. So as the electron density more on donor atom, automatically its donation capacity increases. As its donation capacity increases, then it has to be a strong acid. But this is true up to the compound C. So you can see up to compound C, the pK value go on increasing. That means its donation capacity go on increasing. But what happens? So basicity also increases in the same order. But in compound D, though plus I effect increases, the basicity still decreases. Now you may have a question, why this happened? So let us start the explanation why the tertiary methylamines, trimethylamines are weak bases as compared to primary, as compared to secondary. So the first reason for this is because the basic strength of amine in water is determined not only by the electron availability on the nitrogen atom, but also by the extent to which the cation formed by accepting a proton can undergo solvation and thus become stabilized. So once, what is the role of base? It abstracts the proton from the acid, right? So role of base is to abstract the proton from acid. If the after abstraction of proton from the acid, it gives what? It gives a quaternary salt. So we call it as a cation. So RNH3, that is a quaternary salt, we call it as a, now here a cation. Now cation having a positive charge. So because of that, there is a formation of a bond with the solvent. So water acts as a solvent, and there are three nitrogen atoms, three hydrogen atoms which forms a bonding with the solvent. So as their number of hydrogens are more, naturally this solvation effect is more. So we call this as the effective solvation. So what is solvation? Solvation is responsible for the stability of this nitrogen cation. So this nitrogen cation is stabilized because of this water molecule solvate the cation. Because of this solvation, the stability of this cation increases. So it depends on how many number of hydrogens are attached to nitrogen. With respect to that, number of protons are attached to that hydrogen. So as the number of hydrogens go on decreasing, the solvation effect go on decreasing. So in case of secondary amine, only two molecules, only two solvent molecule form a bond with the hydrogen of which is attached to the quaternary salt, that is in secondary amine, while in case of tertiary amine, only one hydrogen is present which form a bond with the solvent. So as the number of solvent molecule decreases, automatically the solvation effect also decreases. As the solvation decreases means what? This cation is less stable as compared to this cation. So effective solvation means this cation is highly stable. If this cation is highly stable means what? That means it gives extra stability. So not only the whether you increase the electron density on nitrogen atom or not, that is not the only one factor which is responsible for the strength of organic base, but the another factor responsible for this is the how the solvation takes place. So on the basis of this, more the number of hydrogen atoms attached to nitrogen in the cation, the greater is the possibility of solvation through hydrogen bonding. Thus from A to D, the inductive effect of the alkyl group will increase the basicity, but less stabilization of the cation through hydrogen bonding with water. So because of this, there is a decrease of the basic strength, particularly for tertiary amine. So this effect we can see only for the tertiary amine. Such type of effect is not responsible, and now this type of effect is not possible for the secondary amine. Now you may have a question why. So another factor is responsible for this, and that another reason is in tertiary amine, 3-alkyl group causes severe non-bonded steric interaction. So this is a tertiary amine, that this 3-methyl group. So because of this 3-methyl group, there is a severe non-bonded steric interaction. Because of these interactions, then whatever the electron, lone pair of electrons are there on this nitrogen, they are under the influence of cage. So these three alkyl groups forms a cage around the lone pair of electrons. So as this lone pair of electrons are in the cage, though this methyl group increase the electron density on this nitrogen, but at the same time, this three bulky alkyl group forms a cage for the lone pair of electron present on nitrogen. So not the availability, again the capacity of donation, again it decreases. The reason behind it, these two electron, this lone pair of electrons are in the cage. So though the availability of electron density increases on nitrogen atom, but the donating capacity of nitrogen atom decreases. Hence tertiary amines are weak bases. So order of basicity in polar protic solvent is secondary amine is the strong base as compared to primary amine as compared to tertiary amine. So what is polar protic solvent? Polar protic solvent means that hydrogen, polar solvent, in that the hydrogen is attached to highly electronegative atom. Let us, that example for this is water molecule simple, in which hydrogen is attached to the oxygen. So it is a polar protic solvent. Another example can be we can consider is a alcohol. Here also that is the hydrogen is attached to the oxygen. Whenever you use a polar protic solvent, then and then only there is a possibility of solvation. So when solvation takes place, then that time secondary amine is always a strong base as compared to primary, as compared to tertiary. But instead of polar protic solvent, if we select polar aprotic solvent, so what is the example of polar aprotic solvent? A simple example, acetone, in which hydrogen is attached to carbon and not attached to the oxygen. When hydrogen is attached to the less electronegative atom as compared to heteroatom, then it is aprotic solvent. Protic solvent is hydrogen is always attached to the heteroatom. That is called as a polar protic solvent. Here in polar aprotic solvent, hydrogen not attached to the heteroatom. So what happens in polar aprotic solvent? Polar aprotic solvent, there is no possibility of solvation. As the solvation is not possible, so of course the order is now changed. That time tertiary amine is strong acid as compared to secondary, as compared to primary amine. That is only on the basis of electron donating inductive effect increases the basicity. So this is due to no stabilization of cation through hydrogen bonding with the polar aprotic solvent. So this order get reversed because of there is no formation of hydrogen bonding with the solvent. Now this is the next effect. Introduction of electron withdrawing group, that is showing a minus I effect. So for this, that methyl groups are replaced by trifluoromethyl group. So 3 trifluoromethyl groups are there in this example. So as you know, fluorinated compounds, so that is fluoro group is strong electron withdrawing group. So CF3 group shows minus I effect. So because of that, powerful electron withdrawing CF3 groups are present. Due to minus I effect of CF3 group, it withdraw the electron density of nitrogen atom towards itself. So whatever the electron density is there with this nitrogen atom, that is getting attracted towards the CF3 group. So because of that, now there is less electron density on nitrogen atom. As there is less electron density on nitrogen atom, so nitrogen atom not able to donate its lone pair of electron because these electrons are shifted towards the CF3 group. As the donating capacity decreases, the basicity of course get decreased. So groups like fluoro, chloro, nitro, all these groups show electron withdrawing inductive effect. So if such groups are present, then this aliphatic bases or the basicity of aliphatic compound get decreases. Now this is the third factor, that is introduction of electron withdrawing group showing minus R effect with difference in electronegativity of atoms. So what is the meaning of this? So minus R effect is present, which is attached to the nitrogen atom, but at the same time, a minus R effect, in minus R effect, whatever the electron density delocalized, that electron density shared by the atom which is more electronegative than nitrogen. So look at, this is an example of amide. So amides are found to be very weakly basic in water. So look at here. Now NH2, this CO group acts as an electron withdrawing group. So at the same time, it shows a minus R effect. So you can see here how the resonance takes place. The electron pair which are present on this nitrogen that are shifted towards the oxygen, and you can see in the resonating structure, now nitrogen there is a positive charge, so no more electron density with this nitrogen, but oxygen having a electron density now. So whatever the electron density is there with this nitrogen, due to electron withdrawing resonance effect, now it is shifted towards the oxygen. And the point is what? the minus R effect with difference in electronegativity of atom. Nitrogen electronegativity and oxygen electronegativity, that this electronegativity is different. Nitrogen is less electronegative than oxygen. So if that is the case, then this resonance effect, we call it is a more powerful, more effective resonance effect, because the electron density transfer from less electronegative atom to more electronegative atom. So such type effect, such type of resonance, we call it is a more powerful minus R effect. So because of this powerful minus R effect, that nitrogen is now no more electron rich. If the nitrogen is no more electron rich, automatically its tendency to donate the electron pair decreases. Therefore, the basicity also decreases. So that is the major factor. So if the group is present, which is showing a minus R effect, but the electronegativity difference is there. Now, instead of this oxygen, if you have a compound where the electronegativity can be seen, so that is the next point, the introduction of electron withdrawing group showing minus R effect without difference in electronegativity of atom. So this is the simple example where you have a nitrogen electron pair that can be delocalized again towards the nitrogen only. So if that is the case, then what happens? This is an example of guanidine. Look at the pK value is 13.6. So larger the pK value, stronger is the base. Now the effect of delocalization in this case increase the basic strength of the amine. Now why this happen? So first of all, look at the whatever the resonating structure I've shown you over here, that is with respect to the neutral molecule. So guanidine, that three nitrogen groups are attached to the central carbon, and one of the nitrogen is doubly bonded. So this is an guanidine structure. So the electrons which are present on this nitrogen that undergo resonance, and now that negative charge is shared by another nitrogen atom. Again, the electron density present on this nitrogen again undergo delocalization, and it neutralizes the charge on this nitrogen charge, that is a positive charge is getting neutralized. So what you see here, that every time from one nitrogen atom, the electron density shifted to this nitrogen atom. Now from this nitrogen atom, the electron density shifted to another nitrogen atom. So every time, due to the resonance structure, the electron density shared by the same nitrogen atom, in which case there is no difference in the electronegativity. So because of that, what we call this is a, no doubt, the density can transfer from here to here to here, but still having a capacity of that nitrogen to donate the electron pair. So that happens in case of a neutral molecule. But as soon as it accepts the proton from the solvent, so this is converted to cation. So this is a cation. How the cation gets stabilized? By the resonance effect. So you can see the nitrogen electron pair shifted towards this, and whatever the positive charge is generated on this nitrogen after the abstraction of proton from the solvent, so that negative charge is neutralized due to this type of resonance. We call it is a minus R effect. So again, this nitrogen lone pair transferred to the next nitrogen atom, where there is a positive charge. So again, we can show three resonating structure for the stability of this cation. So what we say over here, that this cation is stabilized by electron withdrawing resonance effect. But the negative charge is shared by the same atom. If that is the situation, then the basicity always increases. So because of that, guanidine is a strong base. So how we define this in the, how we will explain these things. In the neutral molecule of guanidine, there is a delocalization of a lone pair of electrons. But in this delocalization, again nitrogen atom shares the negative charge. As there is no electronegativity difference in these two atoms, So any atom can donate its electron pair. Due to delocalization, in this case, there increases electron density, and so it readily donate it and act as a strong base. So that happens in case of a neutron molecule. But what happens after abstraction of proton? The cation again stabilized by resonance effect. Due to stability of conjugate acid, rate of donation of lone pair of electron of nitrogen atom increases. Hence, guanidine is a strong base with pK value 13.6, and larger the pK, stronger is the base. So for this, you refer the books which I have mentioned over here.